Hi there, my name is Miss Townsend and I love math. Welcome to Math with Townsend. This video is for grade 9 academic students who are practicing for the EQAO in June. It's video number 7. In this video, we'll be focusing on motion sensor and distance time graphs. And as you probably already know, when we look at motion sensor or distance times graphs, we're usually looking for direction of motion, distance traveled, time, and speed. So let's look at some questions. Multiple choice first. It says Mark places a motion sensor on a table. He walks slowly towards the sensor, waits a moment, then walks quickly backward away from the sensor. Which graph below best represents his motion? So before I even look at the options, I want to think about what I know. I know that he starts off somewhere. Oops. So if this is the sensor, and so here it is, Mark starts off over here at a certain distance away. I don't know what distance, let's pretend it's 3 meters. Then, a little while later, maybe even seconds later, Mark has moved towards the sensor, and therefore he's now maybe 2 meters away. And then he would be 1 meter away. So when he walks towards the sensor, his distance should decrease. So walking towards something means that your distance decreases, because if you were standing on top of the item, you would be 0 meters away, which is as close as you can get. So if he walks towards the sensor, waits a moment, and then walks away, I'm looking for a graph that does this. Towards, waits a second, away. And if you look, that's definitely what J is doing. So the answer is J. And just to be sure, look at graph F. In F, we're going towards, rest, and then towards still. In H, you're going away, rest, and then away. Definitely not F or H. Look at G. Towards, a vertical line towards. Well, not only is it wrong because it goes towards the sensor, but that vertical line is a real problem. And let me see if I can explain why. At this moment in time, let's pretend that this moment in time is 8 p.m. Where is Mark at 8 p.m.? Well, according to this graph, he's standing right here, but he's also standing right here, and he's standing right here. In other words, at one moment in time, Mark is in several places at once. Now, we both know that's impossible, so you should never see a vertical line on a distance time graph. So it's definitely not G because it breaks the laws of physics. So again, the answer was J because we see walk towards, rest, walk away. So let's look at some other questions. In the morning, Sylvie left home to go to school. The graph below shows her distance from home versus time. So before I even look at what's going on, I like to see the graph. It's measuring distance from home compared to time. So we can see that we start off at home, we move away from home, and then we change speeds, but we continue moving away from home. So we need to go away from home and then continue to go away from home. And the other thing that's interesting is when I change speeds, do I go from fast to slow or slow to fast? Well, a fast line is a steep line, and I can see that the first section is much steeper than the second section. So it goes from fast to slow. So now I'm going to look at the options I'm given. Which sequence of events is best described by the graph? She runs for several minutes, then tires and walks instead. Could be that one. She walks for several minutes, then she turns around and goes home. Well, we know that it's away and then away, so she's definitely not turning around and going home. It's not B. She walks for several minutes, then stops to chat. Well, nowhere is there a horizontal line that indicates a stop in motion. She's never stopped to rest or chat, so it's not C. D says she walks for several minutes, then she sees Ken ahead and runs to meet him. So D and A both are move away, and both of them change speeds. But obviously this one starts off running and then walking, which is fast and then slow, whereas this one is walking and then running, slow and then fast. So I want it fast and then slow, so my answer is A. Nicole rides her bike to school in the morning. She stops at a store for about 5 minutes when she is halfway to school. Which graph below best describes this situation? Now this is, so here, for example, Nicole is riding to school, stopping at the store, but then this would mean she rode back home. There's no indication in this question that she would go back home, so I'm not going to answer F. Here, she goes to the store and then she breaks the laws of physics. So remember that vertical line is not possible on a distance time graph because at this time, whatever time it is, 7 a.m., let's say, she is both at home and she's at the store. That's not possible, so it can't be G. In H, she starts off going really fast and then she slows down. But at no time does she actually stop, so it can't be H. At J, she travels away from home, rests somewhere, and then continues to travel away from home, and that's the one that fits the scenario because this must be where school is, halfway is the store, and here's home. Ride your bike, stop at the store, go to school. So the answer is J. The graph below represents the relationship between distance and time on Javier's walk. How much greater is Javier's speed in section P than in section Q? So remember, speed is your slope when you have a distance time graph. And you should know from science class that speed is distance over time. And if I rise and run, I'm comparing distance over time. Good. So what is his Javier's speed in section P? So we start here at the point 0, 2, and we continue to here, which is the point 3, 14. So either by using the slope formula or by doing rise over run on your graph, find the slope. So the slope is, so on the graph, I rise, I go from 2 up to 14, which is 12, and then I run 3. Same thing you would get if you'd use the slope formula. So this is a slope or speed of 4 meters per second. So let's look at Q. So Q starts at the point 3:14, continues until this point, which is 7:18. So again, either using the slope formula or by doing rise over run on the graph, find the slope. So the slope would be rise 4, run 4. So 4 over 4, that gives me a slope of 1 meters per second. And the question, make sure you always answer the actual question, said how much greater is his speed in section P than Q? So what's the difference between the two? So obviously he is traveling 3 meters per second faster in P versus Q, because 4 minus 1 is 3. Tyler walks along a line leading from a motion sensor. The graph below shows information about Tyler's walk. What is Tyler's speed in meters per second as he walks towards the motion sensor? So the most important part of this question is making sure you remember what it looks like on a distance time graph when someone walks towards an object. In this case, towards the motion sensor. So we know that this, and this are all resting periods, so they're not in contention, obviously. Also, the speed is 0, way too easy a question. So either this is walking towards or this is walking towards. So remember, when you're walking towards the sensor, you're getting closer and closer. So your distance is getting smaller and smaller. So this, when the line goes down, it means you're losing distance, which means you're walking towards the object. So that's the part of the graph that I need to find the speed. So again, I can take the points that represent the endpoints. So one of them is at 3.5 seconds and 4. And the other point here is at 5 seconds and 1. So I can use the slope formula, or I can use the graph. I go down 3 and over 1.5. So the slope would be down 3 over 1.5, and that is 2 meters per second when I reduce it in my calculator. The graph below represents 4 segments of Selena's morning walk. Describe the 4 segments of Selena's walk. So first I'm going to identify the segments because that way I can talk about them easier. So I'm going to call this A, B, C, and D. So looking at the graph, we're measuring time in minutes. And we're measuring distance from home in meters. So I'm looking carefully at the scale. Excellent. And I notice that Selena starts off at home. So section A starts at home. You know what? I'm going to type this. Sometimes the pen just goes crazy. So I'm actually going to be typing this. Woohoo, how exciting for you. Okay, so in block A, she starts at home. And since I'm typing it, I'll try to make sense of this. Selena starts at home. She walks for 5 minutes and travels 300 meters. This is a speed of 300 divided by 5 is 60 meters per minute. Now, what I don't really have indicated is a direction. So I'm going to put just simply, she starts at home and walks away. So the only direction I have, because I don't even know where she's going, the only thing I have is home. So my directions either have to be away from home or towards home. Those are the only options I have. And in this case, she starts at home, so she must be walking away. So look at section B. In section B, well, you can see that it's a flat horizontal line. And if it's a horizontal line, it means that she's not traveling, she's resting. And she rests for 3 seconds from 5 to 8. So I'll say at 300 meters from home, Selena rests for 3 minutes. And you don't have to say speed because obviously she's not moving, but what the heck? It's easy to do, 0 meters per minute. Let's look at block C, or section C. Wait, block C, what am I teaching? So in section C, let me move this temporarily. She goes from 300 meters to 900 meters. So that's 600 meters of travel. And she goes from 8 seconds to 16 seconds. So she's going 600 meters in 8 minutes. And she's continuing to walk away from home. Selena continues to walk away from home. Traveling 600 meters more, taking 8 minutes for this part of part of the journey. Her speed is now, so 600 divided by 8 is 75 meters per minute. And now let's look at part D. So back at the graph, Selena's now got a negative slope, and that means her distance is decreasing, so she's walking home. In fact, she appears to arrive home because here she's 0 meters away. So that's a distance of 900 meters, and it takes her 12 minutes. So let's see. She then returns home, taking 12 minutes to walk 900 meters, and her speed is also 75 meters per minute for this section. Excellent.